All right, hello everybody. I left this graphic up here for a minute, so this is going to be the least AI talk of this entire conference. So I hope it doesn't disappoint you, but it'll probably be the black sheep of all the talks here. This and another image are the only AI related things. I made this with AI, obviously. She did a very good job. I'm here to talk about, my name's Eric Nallon. Black Cow Labs is a small company of mine that focus on this research. I've been doing for about 10 years. This is teaching sensors to smell. So this is really a combination of material science, software, machine learning, and making an end-to-end pipeline for classifying odor. Why should you trust me in hearing about some of these things? I'm really a doubly. That was my background. Heavy semiconductor background, so lots of clean room work, and I worked for the Army for 10 years at Fort Belvoir, where I was really doing IR sensor work, fabrication, but then I got into chemical sensing, trying to make chemical sensors using semiconductor techniques, and naturally, somebody at that time left and did all the machine learning, so I had to learn how to use Python, and that was kind of my entry point into machine learning. And I did my PhD research on using this material called graphene that I'll talk about. All right, so outline is we do a little smell game. What kind of sensing needs are even out there? What is graphene? How can you use it as a sensor? And then getting into sensor data creation, modeling, and then I have examples ranging from volatile organic compounds, that's chemical warfare agent simulants, big thing for defense and military, and then even down to like things like scotch and hot sauces that a human being like to smell. Okay, who smelled essential oils here? They're like everywhere now. You can't go anywhere without it. Scotch whiskeys, a lot of Scotch people in this area. Toluene, benzene, not so much. And then probably the worst of them all. So what I'm trying to show here is like, it's funny to think about essential oils and Scotch whiskeys and things that you can relate to, but these last two, you want something in a very remote environment doing the sensing on its own. Possibly you'll never see it again, or it might self-destruct, sensing things that you'll never as a human being want to smell. So I put 2016 on here because this is a slide that's been unmodified since then. And it's pretty much 10 years later, it is still basically the exact same need. We've progressed, I would say, almost zero. So there's broad application. You see some things coming up in health. You hear about aerospace, like they're trying to put different kinds of sensors in these newer suits, but it's still like, carbon dioxide and things like that. Environmental monitoring is probably one of the bigger ones because there's, heavy metals and things like that are getting in the environment. Obviously, military and homeland, there's all kinds of stuff going on. People are using things like they've never used before. Chemical warfare agents are very hard for people to make, get, and use, but they're called toxic industrial chemicals. It's basically what they use to make plastics and just possibly weaponizing them. So those are still very of high interest. All right, so what is graphene? I'm going to assume basically nobody in here really knows what this is. Carbon has a bunch of allotropes, a bunch of different forms. The one on the very left is called a buckyball. It's a small little carbon ball. They use it a lot in medicine. They use it a lot for like delivering drugs and doing things like that. It's been around for a while. Carbon nanotubes, they've been working with these for a while. Very hard to actually make a reliable device with them because they're very hard to orientate and they're very small, obviously. Graphene is really like taking that carbon nanotube, cutting it, making a sheet, and then obviously we know graphite and diamond. So why graphene has become a lot more popular than carbon nanotubes I'll go over is now you could actually incorporate it into pretty standard semiconductor processing. So now you could scale, make lots of devices, make them small, make a ton of them. Some of the properties, and next slide I'll go over some of the Nobel, there's a Nobel Prize for this. Very interesting properties that were discovered about it, and it's still a very active research area, even though it was back in 2004. Real quick though, because this is kind of foundational to the device itself, is the electronic properties of the graphene, because that's what I'm really kind of after exploiting. It's very strong because all these, that lattice is constructed in that way. So you have a really strong bond like in that plane with the electron. It's very stable and strong. But on the top, these will want to stack on top of each other. And there's kind of this like electron plane. It's an electron cloud because there's this one electron per carbon that's kind of delocalized and it kind of move around. So it makes this cloud. And like that depicted cloud is what kind of gets changed by the chemicals that come in contact with it. Kind of temporarily modifies, and that's what I'm really capturing in the sensor. And then, yeah, last part, graphene's fully exposed. It's a very large surface area, so it can be very sensitive. And then I'll get a little bit more to the selectivity of this and why it's important, because carbon is very good for attaching different kinds of molecules and functionalizing. So there's a bunch of different chemistries you can apply to change the graphene, so it's just a little bit different. Like our olfactory bulb has a bunch of neurons that are all different, and they all respond a little bit differently to smells. All right, so how do you get graphene and make something out of it? So in 2010, there was a Nobel Prize in physics. They used a Scotch tape method. So it's like a piece of graphite, Scotch tape, you've exfoliated graphene. So you've got like a bunch of those layers, they're stacked, you probably had a few of them. And then they isolated it and did a whole bunch of electrical measurements, and they found, wow, this stuff has some amazing properties. That is very hard to do anything with realistically from a product standpoint. So there's a very common method in semiconductors it's been used for a long time. It's chemical vapor deposition. You could make graphene and put it on a pretty large silicon wafer like this person's holding, and now you could start processing that in a semiconductor lab. And if anybody knows that UVA actually has a very world-class semiconductor lab where they allow people to come in and actually do things, just pay for services. So they have a world-class semiconductor lab right here in town. Okay, why is graphene good for chemical sensing? Really, some of those properties I described. Surface, very large surface area. Carbon chemistry means you could apply a bunch of different chemistries or polymers to the sensors to make them respond in a different way, which means you're trying to mimic the human nose, which is not going to be possible, but that's the idea, is to make different. It turns into a machine learning problem pretty quick. You can kind of see. I'll show you some of the time series plots. And really, one of the things that I claim with this is once you create the sensor, it's powerful. Say it can sense all kinds of things. Really, what you need to do is update the algorithm and not the device. So if you had this thing deployed somewhere remotely, you can imagine, oh, I need to retrain it for this new toxic industrial chemical that somebody's using. I'm going to retrain it in the lab, and I'm going to deploy the algorithm, because it's really about that, because the sensor itself is very adaptable to new things. All right, so here's the concept. This kind of sets the stage for the rest of the talk to understand what the data is that we're looking at. It's pretty simple. This is not a transistor. This is it's a resistor. It's a resistor that's affected by the environment around it, because it's basically exposed to its environment. So there's two terminals. We apply a voltage. We're measuring current over time, or resistance. You get into resistance, and you have graphene, and it's under these metal fingers. They kind of look like this. They're called interdigitated, so they don't touch. There's like a gap between them, and that gap is where the graphene is completing the connection. That gap is where the chemical is kind of coming down, like in that figure, and it's influencing the graphene. Now, some chemicals will stick a little bit longer because they want to try to bond to it, but it's inert in ways, so it'll want to come off eventually, and those details of the chemical coming off the surface get captured in the measurement. So now, so really the main concept is the electrical properties are temporarily modified, and that's what we're capturing. Now, if we move down to like the sensor array electronic nose approach, now you have a bunch of these sensors. You apply some kind of surface modification, a polymer, some kind of peptide, various things you could use for biosensing. Now you're getting a different signature for each one of these, and now you can see this turning into a pretty classical machine learning problem where we're pulling features out of time series. All right, fabrication. It's pretty neat. It's actually pretty straightforward in terms of semiconductors. Like, you can do this in a lab with no specialized equipment. But to go over the basics is, you hear about silicon. This is silicon with silicon dioxide and graphene on top of it. You can just buy that. You go on the internet right now, buy a wafer, 6-7 inches for $600 maybe, and you could carry out these kind of procedures. Photolithography, this is really like a pattern. I'm putting a pattern on the surface of my circuits, and then you're going to evaporate metal, so you're going to put metal, and that pattern is going to make the metal circuitry pattern. And then you have a device like this, and now you're bonding it into something that you can actually plug in and start measuring. All right, here's an example of, this is a full wafer that's fabricated. I don't know how many on there, but they're diced up and they're individual sensors. And the nice thing about semiconductors is you can make that design basically anything you want. And these are pretty big, I would say. You can make this much, much smaller than that. You can see these with the naked eye. So the nice thing here is completely customizable. So if you want more sensors, you want to change the geometry for some reason because you believe it's going to sense something better, you can do that. Or you can cram a whole bunch of sensors in there that you can bond to. And the metal there is gold. That's why it's titanium and then gold on top. All right, so kind of moving away from the device itself, what the device is, getting into more of like, okay, now we have the device. What are we going to do with it? So these are some pretty typical steps of somebody doing some data science work or exploratory data analysis, getting towards doing some classification or regression problems. Kind of focused in on the feature extraction portion more than all the others, because this is really the important part for this, because there's this very important chemical information kind of encoded in that time series plot. I've kind of broke down three larger areas here. Traditional feature engineering. This is when like you have somebody that, like a chemist, if a chemist knows certain things about, like, oh, I want to pull these certain things out of here because I understand these kind of features, you might encode like very specific feature engineering pieces. If you read literature for this kind of work, very common is like, max change in resistance, the areas that are inside of those red and green areas. Those are pretty common features that you would see. I'll show some results from a paper on the next set here. Is I modeled just that response or that response and recovery area, like when the analyte hits and is responding and it recovers, trying to get those exponential fitting coefficients, because it's believed that when the chemical is coming in contact with the graphene and it's coming off, there's that interaction is a physical chemical interaction that you can model and get some parameters that way. And then some more, more modern ways of like automated feature extraction. Like, let's just send the time series through a one-dimensional CNN, or let's do an autoencoder and pull things out in an automated way. All right, so the top here we have maybe three techniques. You're gonna do those parameters, as I call them. Maybe you just subsample it. This is sampled pretty quickly, so maybe you just subsample the response and feed those right in. And then the last one was that, what I call like transient fitting, so we're fitting the coefficients. So pretty traditional way to get your feature vector. You have measurements going down the rows, and across the columns you have all the features. But I think the big question is, how do you get this data? Like, how do you make chemical sensor data? And I was trying to describe this as second AI image. ImageNet, right? Like modern computer vision algorithms, a lot of them are really use that ImageNet data set. It's huge. It took a long time to curate, but there's a lot of human beings around, and everybody's always curating data, whether they know it or not. But what is kind of the analog in the odor space? And that just doesn't exist. Mainly because there's not a need for this, but eventually I believe there will be a need. Somebody's going to want to make these kind of sensors and do this sort of thing. So there's no way to actually collect and make labeled training data. This image is pretty funny because this guy over here is smelling some things, and there's like coffee beans and an orange and a bottle of gas. So AI just put that together. I mean, it did an amazing job. I would never be able to make this, and it was a pretty good depiction. But I thought that little detail was really funny. The open bottle of gas. It looks bad. All right, so collecting the data for this. So this is a piece of hardware that I built. What this is, it's a fully automated collection system. and it's made to be pretty simple. It's made to take an input file where just in the input file you say, these are my sample sequences. Like I want to sample air for 60 seconds, and I want to sample the chemical for 30, and then I want to recover with air for 120 seconds. I want to do this 50 times, and then inside my vials here on the right are these kind of compounds. And this is all built with just off-the-shelf stuff, Raspberry Pi, mass flow controllers, which are controlling the airflow pretty precisely, and data acquisition, and then web relays. So all of that's Teflon to try to avoid things sticking inside of the tubes, even though you can change everything out. And really what you get out here is CSV files. Each file is labeled a single data set. So it'd be one time series piece of data with all the data elements in there labeled with that particular compound. Here's an example of a YAML file that you may load where you would tell things like, you could also change the concentration. So if you want to say, I want to do a concentration experiment where I want to change the concentration I'm going to introduce to the sensor in various ways because I don't want to give it full concentration, you can do that. And then this is where you define the repeats, what's in the vials, and then also at that point you have CSV files that are labeled. Like the machine learning part of this now is pretty straightforward to do evaluation on. I have a patent pending on this. This is pretty close to being complete. So that was a prototype. This is still a prototype, but it's very similar kind of look here, a bunch of 3D printed parts and mass flow controllers, a microcontroller, and kind of that same concept that I described before as a file, input file in, and then a bunch of training data out, and then this thing in between where you could change out the vials. You could actually put solid sources in between it too. So if you have something that's not liquid, you could put that in a tube and you can use that as a source. All right, so that's the training system. How do you make the data? So what do you do now? What are the things that people ask about in this field? A big one is concentration. So that top left plot, what you're seeing is 3 chemicals exposed a number of times, but the concentration is being decreased every time. And what you're seeing in the PCA, that 3D plot, is they're all kind of converging in one spot, which is saying, okay, you have a really hard time deciphering these chemicals at low concentration. They're all converging to about the same thing. And you can look, if you look at the time series plot, they're very similar shapes. The magnitude is definitely different, but like that's not going to get you very far when you go to low concentration. So you're going to start looking really similar. Stability studies is another thing everybody asks, like how stable is it? How long is it going to fail? How long is it be until it's useless? You can do things like just randomize the order of these measurements and do 360 measurements total and start looking at, in this case it was the change in resistance normalized over time. So seeing like how stable is the response over time when I'm repeatedly exposing the sensor to a chemical and then other chemicals in different ways. And then obviously the machine learning part. This really enables that. That's the main piece. And this goes well with adapting to new compounds. Because if you have a system like this, you could plug in new compounds and you can make new training data, update an algorithm. Okay, so some results to go over. This is a paper from a while ago in ACS Sensors. So what I really want to explore is like, what does bare graphene as a sensor do? Like, what is it capable of? So nothing's been modified, it's just a sensor. There's no surface modifications. So this is like, I chose this chemical set. It's very broad. There's like all kinds of different structured compounds, electrical properties. There's 20 measurements here of each one. I think the really interesting observation from this was on the left-hand side, like look at the diversity and the responses from the different chemicals. You have resistance going up, resistance going down. There's electrical changes happening. They're very different across the compounds. Now you see some of them are very similar, like we have nitrotoluene and chlorotoluene. So both toluenes been functionalized with different things. They do have some definite similarities, but they also have some nuances to them, like when they recover or when the response happens, and that's really that transient information. That's like the really feature-rich information. I put these notional boxes around here to kind of try to group things, but without rotating this, it's a little hard to see here. Okay, kind of a next set of experiments for that same sensor, unmodified, is how well does it do when you introduce it to things that are extremely similar? So a few things that are very similar, some of these compounds at top, these are isomers of each other. So these two xylenes, like you're literally just changing, it's the same exact formula, but you're changing the position on that benzene ring. So these are very similar. Some of them even down to their molecular mass, their electronic structures, very, very similar. So let's say 18 measurements each of each one. You're looking at the change in resistance over time from 2D. Very confusing. You might be able to pull apart the mesostyrene and the toluene based on the max change in resistance, but you start changing the concentration here, you're not going to do very well. So what I wanted to try here is try to prove the concept of pulling out those fitting coefficients. So the experiment was create two feature sets. Create one with kind of these more traditional change in resistance, grab the area. The area does kind of capture some of the transient information. Make that feature set A. Now feature set B is that plus the fitting coefficients. Now you have the data. You don't have to take any more measurements. Now you have the data. It's really just coming down to doing some experiments with this. All right, so pulling out those fitting coefficients in those equations there, what I was really trying to show is use random forest. I wanted to use that because I wanted a way to actually look at the feature importance that was contributing to the classification. And there was a pretty clear divide between the contribution of the features in the first data set and the second, particularly those exponential fitting coefficients were very indicative of it classifying them correctly. And then the last slide for this particular experiment is, if you were to plot these in 3D, in the first case for PCA, it's just a three-dimensional plot because there's only 3 features. And in the second one, adding the additional features, get much better clustering. First case, possibly the mesostyrene and the toluene you'd be able to pull apart, but on the second one with the additional features, get much better clustering, and then that translates directly into better classifier performance. All right, so we talked about what graphene is, how do you make a graphene sensor, how do you collect data, what can a graphene sensor do on its own that hasn't been modified at all, no surface chemistries. But really what you're seeing in some of those examples are, you can start doing some tricks with data, but eventually you run into, I want to classify 50 different things with this one sensor, and it's going to struggle. So a solution to that is to make an array of these sensors. So it's only going to get you so far with a single sensor. So idea here is make an array of many sensors, nothing near the complexity of a human being. Millions of different neurons that kind of react in different ways. In this case, there's 24 sensors in this array, so that's kind of that pattern design I was talking about before. You use that, so you design that in CAD software, and then photolithography, they make something called a mask. It's made out of glass, and it has that design on it, and then you press that against the semiconductor wafer, and it has photoresist on it. It's just like photography, just at a very micro scale. It's the exact same thing, actually. And you deposit your gold and you lift it off. Right-hand side, you can see like the kind of dimensions we're dealing with here. So this is a scanning electron microscope image, and those thin traces, those are metal. So that's the gold, and then in between those is the graphene with the polymer on top that's been applied. So we're at like 25 microns now. 50 microns is like a hair. So that's the kind of dimension. This is pretty big, I would say, for like this kind of thing. This is micro, not nano scale. So you can go much, much smaller if you needed to. All right, so how do you really like engineer this the array of response? There's, I don't know how many polymers are out there. I'm not a chemist, but there's a lot. You can go on Sigma Aldrich, and it's overwhelming, everything that's out there. But working with some chemists that could help figure these things out is picking out a panel of polymers. Part of this is an experiment to see which ones, you want ones that like really broadly respond. You don't want like 5 sensors that respond in almost the same way. So picking out that, and also what kind of, they have to be put in a solvent. So realistically, how do you get that onto the sensor? It's usually done by drop casting. If you're making these just in a lab, it's done by hand, where you're just drop casting polymers from a vial onto the sensor using a very small specialized pipette, and putting on a hot plate and letting it cure. If this was made in a factory, it'd be probably more of a microjet technique where they can put them on. But idea here is commercial polymers, they're in a solvent, you're putting them on top of that array to make them all different. Here's a zoomed in picture of that sensor. So there's the dimensions of the sensor there. Just put a few things up there, like 50 microns, it's white blood cell, human hair, pollen, kind of like that kind of size. And again, this is big for this area of semiconductor processing. Like, you see this mostly with your eyes. It's a little hard to see. I think you can see it from there. These are gold wire bonds. So those little pads of gold, there's also a very thin gold wire bond, and that bonds out to the inside of this chip carrier. So now you can plug this thing in and actually measure it. I've done all of those by hand and many more. It's excruciating. And then
24 little droplets.
Yeah, there's actually one is bare. You'd probably want to keep a couple bare as like a control. But yeah, you can kind of see some of the polymers, especially the upper left, but those are the dropped polymers on each one. All right, here's a little GIF of so this is chloroform. This is just 4 sensors from, it may have been that array, I'm not exactly sure. But you can kind of see what the response time, this is actually measurements, but this is pretty quick. This is happening within sub-second, half a second to a second response. So it's pretty quick. So you can see, this particular channel, the aqua color responds very aggressively towards chloroform, and these other ones not as much. And then it doesn't actually capture the recovery part, but that information is just as important, because some of these take a long time to recover or longer, and some of them are like almost instantaneous. So all of that together is what really goes into the algorithm. All right, so getting into some results with other things. Chemical warfare agent simulants. You can't get chemical warfare agents, and you should not be able to. But there are things out there that kind of mimic them. And in general, they are organophosphates. So if you hear in the news, Roundup, and there's organophosphates in breast milk, and there's organophosphates in your food, it's from Roundup. And then also, chemical warfare agents are a derivative of an organophosphate. So these, the compounds I have with the red arrow, these are, commercially available chemicals that are similar in structure. So it's the closest thing you can get to kind of mimic like a sensor. They're not, I wouldn't recommend smelling them, but they're not like a chemical warfare agent. And then a bunch of interference. So Roundup. Other things you might like encounter in the environment, like hexane. Sometimes that's with fuel. Ethanol is another common one. Acetone, places do cleaning, or diesel fuel. Toluene is another cleaning, and just water. So in this case, you see, I can't remember how many measurements there were on these ones, but there's quite a few. These are 4 sensors out of the whole array that pulled out that had some pretty interesting time series profiles. So I think we all probably take this for granted. You take all the data, you plot it in 3D, use PCA, use TSNE, use these techniques, and you start looking at clusters. But a lot of people in this field are chemists, and they don't do a lot of programming. They don't do a lot of data science work, heavy Excel users. So what this is like trying to show somebody, like, how does the sensor perceive what a chemical signature is? Like, why does it confuse this compound with this compound? And you can start showing them visually, like, okay, if you want to look at the data, this is really like kind of what the sensor's smelling when you look at different clusters. But also, it's a good way to like tweak things, like, oh, I want to interactively just tweak all my pre-processing and see what kind of results I can get out of it. So something like you can do in a lab, or somebody that's creating a new algorithm for this. So here's another GIF of a dashboard. So you can load data on the left, and then you can choose pre-processing techniques. So it's really doing the raw data, pre-processing, like normalizing the time series. There is some drift correction that has to be done on all of these because there is some drifting. And then at the very bottom on the left, you can't really see, but there's a feature exploration. So you want to maybe try choosing different features to see if you can get a better distinction. But yeah, this was really handy actually to make this and be able to plot it and zoom in. This is all Plotly. This is all Python. To be able to zoom in and kind of look at each cluster and determine which one is and turn them on and off. All right, so a few more slides here. Most people are they like to see something they can relate to. So I think at this point in time in my life, there's a whole bunch of hot sauces in the refrigerator. So a bunch of really common hot sauces you can buy at any grocery store. I was curious to just see how the sensor would do. Because with that training system, it's really okay, load them in a vial, get the tubes in, and kind of replace them. Training file, update that, collect data, start analyzing. So yeah, the hot sauces were fun. Did essential oils because it's almost like anybody could relate to, and it's everywhere. I think essential oils are in everything. And a human being is extremely sensitive to an essential oil. Maybe not as much as a hot sauce, but somebody opens essential oil, you're gonna probably be able to smell it. All right, so everybody loves this one. My neighbor at the time had a whole bunch of scotch because he's in the Army, and I was over his house, and I was smelling a few of them, and I'm like, oh wow, these smell this one smells like a campfire, and this one smells like this. And for any of the Scotch people in the house, that really peaty smell is this one on the top right is these phenols. To me, it smells like a Band-Aid, an antiseptic. If you go to a hospital and you wash your hands, that's an antiseptic hand wash. And you go look in the ingredients, and it's the phenols. And those come from smoking the peat. When they smoke the peat, the phenols come off and they go into it. And that's what you're really smelling. So those are the things that the sensor would pick up. Those are the nuances. So kind of back to the original experiment. It's what would happen if you just put this bare graphene sensor against these scotches plus ethanol? And it does not do very well. The ethanol, I think, is having some drifting there. I think if you look at the shape of it, it's really the same shape. I believe that it was a concentration thing. But if you look at the rest of the scotches, there's almost no distinction between them. They almost look identical. So if you go ahead and add one, in this case, one sensor that's been, one sensor with a particular modification, the one that performed pretty well. You see now we actually have a flip in the response of the ethanol. And to me, I think you're starting to get at some of the distinguish some of the smell component of those scotches now, and you're isolating the ethanol away from it. Now you could actually start getting some of the features out. This was with just one, so I think it would even do better, or be able to do more scotches with further sensors. Okay, conclusions are these rays are really turning odors into a measurable thing that you can measure and then do something with. And on top of that is there's no current way to actually get data like this. It's not like computer vision, but there's no need right now for something like this like there is for computer vision. So there's sort of a critical part of how do I generate that data so I can start doing the algorithm work. And nobody wants to create hardware all the time, especially the military. You want to make hardware and you want to update it if you can. So the idea there is if you make something that's robust and powerful, and that's a chemical sensor, you could retrain it in a laboratory and update the software, update the algorithm, and leave the sensor the same. So that's kind of the key point there. Okay, that's it. Any questions? Okay.
If you have a sensor out in the field, if it's just sitting in a cloud of a gas that it's exposed to all the time, would you have to have a supply, a little canister of fresh air or something to flush it to be able to do this sample and recovery?
In that case, probably. I would say that's an atypical example of having a place that's constantly in that phase. More of it is the Army isn't really interested in making these microsensors like these and just dropping them from small drones and having them in a network, and then they could pick up like a plume as it passes by. In that case, yeah, it would be hard. Honestly, if it was in that for too long, it would probably foul it. I mean, eventually the sensor's going to foul, and it's not going to recover back to its normal enough state to be able to do its classification accuracy as it should. And I think at that point is where there'd be built-in algorithm to say, this device is untrustworthy now. It's not meeting any baseline tests.